Hey students, let me try a video solution. This is from your chapter 19 on electric potentials, but it's from the harder book, the university physics book. And I guess that's chapter, let me look here, I guess that'd be chapter 7 in the university excuse me, book. But anyways, it's number 91 here. And it's an interesting problem. Actually, both simple and clever, and I guess that's what makes it a hard problem here. It says a uniformly charged half ring. All right, so let me draw a half ring. And that's not a very good half circle, but I'll go with it. Okay. And I'll put a little dot here for the center. But it says uniformly charged half ring of radius 10 centimeters, I'll convert it to meters, is placed on a non-conducting table. It is found that 3 centimeters above the center. And so coming up and out of the paper, maybe I'll use this little pointer, which is a little screw here pointing upward. But right here at the tip of the screw is really the distance they're talking about. So it says, it is found that 3 centimeters above the center of the half ring, the potential is a negative 3 volts with respect to 0 potential at infinity. Okay, how much charge is on this half ring? All right, so what, of course, makes it look a little bit harder here is it's this continuous charge that kind of smells like a bunch of calculus to me. Let me put this off to the side for a moment. Let me look a little chunk here of charge that's on this ring. Let's call it dq. And let me just remind you of the point of the 19 is the electric potential, but we learned that the electric potential from a point charge is given by this equation, where we have Coulomb's constant, the charge, and then the distance away. So if we applied it to this little chunk right here, we might then say something like this, and maybe I'll switch back over to red. But this would be then, and I'll call it a little potential from that little chunk of charge. And of course, there would be another chunk of charge next to it, and another next to it, and another next to it, and so forth and so on. And so here's kind of where the calculus, sort of calculus, comes in, because we would say that the total potential then is what you get when you add up all the potential from the individual pieces. And so that's the calculus part. That's the part where you got to think that, okay, what is an integral? And an integral is a summation. All right, so I'm integrating this dq dr. But it turns out for this one, if you give it some thought, you don't even really do the integral. You may think about it in the process, but just think of it as a summation, because then again, watch this. And so we've got v, okay, for the potential. And then if we say, let it kind of at least mentally think about adding up a bunch of chunks of charges, okay? And as we do that, the Coulomb's constant can be pulled out in front because it's the same for every little chunk of charge. And here's what makes the problem interesting is the R. R is actually the same distance away. Let me put the little screw back up here. And you'll see that this distance upward of 3 centimeters and this distance radius outward of 10 centimeters, maybe I'll draw kind of a cross-sectional view, so 10 centimeters out in radius and 3 centimeters up would make the distance along a hypotenuse. And so the distance from the top of this screw down to this chunk of charge is actually the same for every chunk of charge. And so I could actually then say, let me just pull out the R. And that's really kind of the magical step. Because once you do that, you can then just say, well, what does this actually mean? This means add up all the chunks of charges. So let me just call that capital Q. That's just all the charge on this half a ring. And there it is. How much charge is right there on that half a ring? That's what we're looking for. And now we have a fairly easy equation. This number right here is negative 3 volts. Coulomb's constant, of course, is 9 times 10 to the, ninth, plus 9. And the units are a Newton, a meter squared over a Coulomb squared. There's Coulomb's constant. The other part here is this distance away, and let me come back to this profile view, or this cross-sectional view, and do a Pythagorean theorem. So it's 0.1 squared plus 0.03 squared square rooted. And that would be in meters. And then, of course, you also have the Q here. So if I do my numbers here, and so I'll do this side of the equation, negative 3, and then I'll say times, and I'll bring this over because this is then the square root of 0.1 squared plus 0.03 squared, and end of square root. Then it would be divided by this number, 9 times 10 to the 9th, and you would get a Q of negative 3.48 times 10 to the negative 11. And it would come out to be coulombs. I suppose we should work that out. Let me do the units over here. This would be a volt times a meter from over here. Then this would be a coulombs squared when I bring this, which I can think of it as downstairs, on over. And then over a Newton and a meter squared. And so one of the meters cancel off. Then I can think of the Newton meter as a joule. I can also think of the volt as a joule per coulomb. And so the 2 joules cancel off, and one of the coulombs cancels off, leaving me with coulombs. All right, so it wasn't a real hard problem. It wasn't really even some calculus. It was maybe thinking with calculus. And then actually doing the calculus was pretty straightforward. All right, hope that would help.